Hello, my name is James, and I'll be presenting our work, Evidence Accumulation in Deep RL Agents Powered by a Cognitive Model, as part of the NeurIPS 2022 MemARI Workshop. Substantial evidence from neuroscience suggests that the brain represents task-relevant physical and abstract variables in a structured manner as cognitive maps, with different neurons being tuned to, say, specific positions relative to an object, or specific amounts of time since the salient event. Inspired by this, we sought to demonstrate that an artificial neural network, given the right architecture, can form representations that resemble neural recordings observed in mouse brains, and that such representations can be beneficial for learning the behavioral task. In a recent study, Nia et al. Presented mice with a virtual track where objects appeared on the left and the right-hand side of the wall. At the end of the track, mice had to turn left or right depending on which side had more towers. Nia et al. Demonstrated that hippocampal neurons tuned to the magnitude of the task-relevant variable, which is in this case the difference in count between objects on the left and objects on the right-hand side, which they referred to as evidence. To train artificial agents, we designed a simplified version of the accumulating towers task. This simplified environment consists of a virtual track composed of three inputs, left, right, and middle. The agent moves down the track and observes towers, represented by the input changing from 0 to 1, on either the left or right sides. At the end of the track, the agent receives a reward if it chooses either the move left or move right action, depending on which side had more towers. Our network architecture is based on a simple RNN, but with analytically derived weights that work together to represent the number of towers at any point in time. The computations involved can also be viewed as an approximation of the Laplace transform. Once we have that representation of the Laplace transform, we can also add a linear transformation that inverts the Laplace transform. This results in neurons tuned to different numerosities, which we call f tilde. Additionally, having access to the Laplace domain lets us compute the subtraction of two numerosities to represent the evidence axis. All the agents we tested were based on the actor-critic architecture, with the actor and critic networks each being a single fully connected layer. We tested the Laplace framework methods, with ablations removing the subtraction component, the inverse Laplace transform component, and both components. And we also compared our models to a simple RNN and a GRU, both with unconstrained trainable weights. Note that the RNN-based component of our agent has no trainable parameters. As a result, our agents had 2 to 3 orders of magnitude fewer parameters than simple RNN and GRU-based agents. We found that our f tilde subtraction agents were the first to solve the task and converged to an average reward value of 10, followed by our f subtraction agents. This indicates the importance of the subtraction operation. Additionally, while the GRU agents were able to learn the task nearly as well as our agents, the simple RNN agents performed significantly worse, hinting that gating may be important for correct performance. Additionally, the activity of the neurons in our agents resembled the neural recordings of the mouse hippocampus observed by Nia et al. Thank you for your time, and please reach out to me with any questions.